The universe played a trick on us. It made itself incomprehensibly vast, then capped our maximum speed at something laughably slow. The speed of light sounds fast until you realize it turns our galaxy into a maze with exits trillions of kilometers apart. Alien civilizations might be watching us right now, but the universe has built a wall between us that makes physical contact almost impossible. If you're curious about the universe, hit that subscribe button. It really helps us bring more cosmic stories to your screen. Now let's begin. Let's start with something familiar, our cosmic neighborhood, the solar system. The Sun sits at the center, a massive ball of hydrogen and helium undergoing nuclear fusion, pumping out light and heat that makes life possible on Earth. We orbit about 150 million kilometers away, a distance we call 1 astronomical unit. Light from the Sun takes about 8 minutes and 20 seconds to reach us. Think about that for a moment. The warmth you feel on your face from sunshine left the Sun's surface more than 8 minutes ago. You're literally feeling the past. If the Sun suddenly vanished right now, poof, gone in an instant, we wouldn't know it for 8 minutes. We'd still see it shining in the sky, still feel its warmth, completely unaware that our star had disappeared. This isn't science fiction. This is the reality of living in a universe governed by the speed of light. But Earth is relatively close to the Sun. Let's travel outward. Mars, that rusty red world that captivates our imagination and drives our exploration efforts, sits about 228 million kilometers from the Sun at its average distance. Light takes roughly 12 minutes and 40 seconds to get there. When NASA's Perseverance rover sends a signal back to Earth, that message travels at light speed, and depending on where Earth and Mars are in their respective orbits, the delay can range from about 4 minutes to over 20 minutes. This means that when engineers at the Jet Propulsion Laboratory in Pasadena, California, send a command to the rover, they have to wait at least 8 minutes for a round trip at best. There's no real-time control. Everything must be planned with this delay in mind. Journey further out to Jupiter, the king of planets, a gas giant so massive that more than 1,300 Earths could fit inside it. Jupiter orbits about 778 million kilometers from the Sun. Light takes roughly 43 minutes to travel from our star to Jupiter's swirling cloud tops. The Juno spacecraft, which arrived at Jupiter in July of 2016, operates under similar communication constraints. Commands from Earth take over 40 minutes to reach the probe, and its responses take just as long to come back. Now venture to the edge of our planetary system, to Neptune, the distant ice giant with wind screaming across its surface at over 2,000 kilometers per hour. Neptune sits approximately 4.5 billion kilometers from the Sun. Light from our star takes about 4 hours and 10 minutes to reach this frigid world. When Voyager 2 flew past Neptune in August of 1989, the only spacecraft ever to visit this distant planet, its data transmissions took over 4 hours to reach Earth, traveling at the absolute cosmic speed limit. And we're still in our own solar system. We haven't even left home yet. The edge of our solar system is defined by different boundaries depending on who you ask. The Kuiper Belt, that region of icy bodies beyond Neptune where Pluto resides, extends from about 30 astronomical units to 50 astronomical units from the Sun. Light takes between 4 and 7 hours to cross this region. But some scientists consider the true edge of the solar system to be the heliopause, the boundary where the solar wind from the Sun finally gives way to the interstellar medium. Voyager 1, humanity's most distant spacecraft, crossed this boundary in August of 2012 at a distance of about 121 astronomical units from the Sun. Light takes roughly 16 hours and 40 minutes to travel that far. Voyager 1 launched on September 5, 1977, nearly 5 decades ago. It's been traveling through space at about 17 kilometers per second relative to the Sun, which sounds phenomenally fast. That's over 61,000 kilometers per hour. At that speed, you could travel from New York to Los Angeles in less than 4 minutes. But compared to light speed, Voyager 1 is crawling. It's moving at only 0.0057% the speed of light. 0.0057%. After nearly 50 years of continuous travel, Voyager 1 has barely left the solar system. And it's never coming back. It will wander the Milky Way galaxy for millions, perhaps billions of years, a silent ambassador from a small blue world orbiting an average star. This is where the true scale of the universe begins to sink in. The stars we see at night, those twinkling points that have inspired poets and scientists alike for millennia, are incomprehensibly far away. And the speed of light, as fast as it is, becomes the chains that bind us to our cosmic island. Let's talk about the nearest star system to our Sun, Alpha Centauri. Actually, it's not a single star but a triple star system consisting of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. These stars are gravitationally bound to each other, dancing through space together in the southern constellation of Centaurus. Alpha Centauri A is slightly larger and brighter than our Sun, with about 1.1 times the Sun's mass and 1.5 times its luminosity. It's a G-type main sequence star, yellow like our Sun, burning hydrogen in its core. Alpha Centauri B is smaller and cooler, a K-type orange dwarf with about 0.9 times the Sun's mass and less than half its brightness. These two stars orbit each other every 79 years, swinging as close as 11.2 astronomical units and as far as 35.6 astronomical units apart. For reference, 11.2 astronomical units is roughly the distance between the Sun and Saturn, while 35.6 astronomical units is a bit beyond Neptune's orbit. Then there's Proxima Centauri, a tiny red dwarf star, dim and cool, with only about 0.12 times the mass of the Sun. It's so faint that despite being the closest star to us, you can't see it without a telescope. Proxima orbits the binary pair at a distance of about 13,000 astronomical units, which equals roughly 0.21 light-years. That's about 430 times the width of Neptune's orbit around the Sun. And here's the key fact: Proxima Centauri, our nearest stellar neighbor, sits 4.245 light-years away from us. Let that sink in. The closest star to our solar system is over 4 light-years distant. That means light, traveling at 300,000 kilometers per second, takes more than 4 years to bridge that gap. The light you see from Proxima Centauri tonight actually left that star over 4 years ago, when it was still 2021 or 2022 here on Earth. In more tangible terms, Proxima Centauri is approximately 40 trillion, 200 billion kilometers away. That's 40.2 trillion kilometers. Written out, that's 40 million kilometers. Our human brain simply didn't evolve to comprehend distances like this. We can write the numbers, we can do the math, but truly grasping what it means is nearly impossible. Remember Voyager 1, traveling at 17 kilometers per second? At that speed, it would take roughly 73,700 years to reach Proxima Centauri. 73 millennia. Modern humans, Homo sapiens, have only existed for about 300,000 years. Written language has only been around for about 5,000 years. The entire span of recorded human history would fit into the journey time to our nearest stellar neighbor with room to spare. And Proxima Centauri isn't some exotic destination we've chosen arbitrarily. It's literally the closest possible star. Everything else is farther away. Much farther. Let's look at some other nearby stars to get a sense of our stellar neighborhood. Barnard Star, a red dwarf in the constellation Ophiuchus, lies about 6 light-years away. Wolf 359, another dim red dwarf, is 7.8 light-years distant. Lallan 21185 sits at 8.3 light-years. Sirius, the brightest star in Earth's night sky, that brilliant beacon in the constellation Canis Major, is 8.6 light-years away. These are our neighbors. Our cosmic block, if you will. And even traveling to the closest one would take tens of thousands of years with our current technology. Now, you might be thinking, okay, but technology improves, right? We've gone from the Wright brothers' first flight in 1903 to landing on the moon in 1969. That's just 66 years. Surely we can develop faster spacecraft? And you'd be absolutely right that technology advances. But there are limits, hard limits imposed by the laws of physics themselves, and the speed of light is one of them. According to Einstein's special theory of relativity, published in 1905, nothing with mass can reach or exceed the speed of light. Not almost reach it. Not get really close. Actually reach it. It's impossible. As an object with mass approaches light speed, several things happen. Its mass effectively increases, requiring more and more energy to accelerate it further. Time dilation occurs, meaning time passes more slowly for the moving object relative to stationary observers. And the energy required to continue accelerating approaches infinity as you approach light speed. This isn't a technological hurdle we might overcome with better engineering. This is the fabric of reality saying, no, you can't do this. It's like asking if we'll someday build a machine that divides by zero or creates a square circle. The question itself is based on a misunderstanding of what's possible. But let's imagine, just for a moment, that we could somehow build a spacecraft capable of traveling at 10% the speed of light. That's 30,000 kilometers per second. Outrageously fast by any standard we currently have. At this speed, you could travel from Earth to the Moon in less than 13 seconds. You could reach Mars in under 8 hours at its closest approach. This would represent a million-fold improvement over Voyager 1 speed. Even at this incredible velocity, reaching Proxima Centauri would take over 42 years. An entire human lifetime, assuming you left as a young adult. You'd arrive as an elderly person if you lived that long. And that's assuming constant velocity with no time needed to accelerate or decelerate, which isn't realistic. Let's push further. Imagine 20% light speed, 60,000 kilometers per second. This is entering the realm of science fiction with our current understanding, but let's dream. The trip to Proxima Centauri drops to about 21 years. Still more than 2 decades. Still requiring life support, food, water, and psychological endurance for a crew that would spend their young adult years traveling through the void. What about 50% light speed? 150,000 kilometers per second. Now we're really in fantasy territory, but the journey time drops to about 8.5 years. Nearly a decade, one way. No turning back. No resupply. No rescue if something goes wrong. To visit Proxima Centauri and return to Earth at 50% light speed would take 17 years minimum, not counting any time spent at the destination. Your friends and family would age 17 years. Children would become adults. The world would move on without you. And here's something even more sobering: Proxima Centauri might not be worth visiting. Recent observations have confirmed that Proxima Centauri has at least 2 planets. Proxima Centauri b, discovered in 2016, is roughly Earth-sized and orbits within the star's habitable zone, that Goldilocks region where liquid water could theoretically exist on a planet's surface. When news of this discovery broke, headlines proclaimed Earth-like planet found around nearest star, and speculation about life exploded across media outlets. But here's what the headlines often glossed over: Proxima Centauri is a red dwarf, a type of star known for violent stellar flares. These flares blast the surrounding space with intense radiation, X-rays, and ultraviolet light far more powerful than anything our Sun produces. Proxima Centauri b orbits very close to its star, only about 0.08 astronomical units away, because red dwarfs are so dim that the habitable zone sits much closer in. This proximity means the planet is constantly bombarded by radiation from stellar flares. Additionally, planets orbiting so close to their stars become tidally locked, meaning one side perpetually faces the star while the other side remains in eternal darkness. One hemisphere bakes under constant starlight while the other freezes in permanent night. The temperature gradient between these two sides would create devastating wind patterns, possibly stripping away any atmosphere the planet might have had. Current models suggest Proxima Centauri b is unlikely to be habitable, at least not in any way we'd recognize. It might be a barren, radiation-scorched rock with no atmosphere, no water, and certainly no life. We won't know for certain without sending a probe there, but the prospects aren't encouraging. So even our nearest stellar neighbor, the one star system closest to us in the entire universe, might offer nothing of value after a journey of decades or centuries. And beyond Proxima Centauri, the distances become even more crushing. Let's expand our view to stars within 25 light-years of Earth. This sphere of space, 50 light-years in diameter, contains roughly 130 stars. Most of them are red dwarfs, small, dim, and prone to those violent flares we mentioned. Several are white dwarfs, the dense remnants of stars that have exhausted their fuel and collapsed. A handful are sun-like stars, potential candidates for hosting habitable worlds. But 25 light-years means even at 10% light speed, a journey of 250 years one way. At 1% light speed, which would still represent a tremendous achievement, we're talking about 2,500 years. Think about where humanity was 2,500 years ago. The Roman Republic hadn't been founded yet. The Greeks were just beginning their classical period. The Buddha was teaching in India. The entire span of Western civilization, from ancient Greece to the modern day, equals the time it would take to reach a star 25 light-years away at 1% light speed. And most stars are farther than that. Much farther. The Milky Way galaxy, our home galaxy, contains between 100 billion and 400 billion stars. Recent estimates suggest about 250 billion plus or minus 150 billion. That's an uncertainty range larger than the entire number of stars we once thought existed in the galaxy. Our galaxy is a massive disk about 100,000 light-years in diameter and about 1,000 light-years thick, with spiral arms wrapped around a central bulge and a supermassive black hole at its core. Our Sun sits about 26,000 light-years from the galactic center, roughly halfway out along one of the spiral arms, the Orion Arm. We orbit the galactic center at a speed of about 230 kilometers per second, taking approximately 230 million years to complete one orbit. The last time our solar system was in this position in the galaxy, dinosaurs were just beginning to diversify on Earth. In this vast galactic disk, stars are separated by enormous distances. The average distance between stars in our region of the galaxy is about 5 light-years. In the denser regions near the galactic center, stars might be separated by only 1 light-year or less. In the sparse outer regions, 10 light-years or more between stars is common. But even 1 light-year is an immense distance. Even 5 light-years is crushing when you consider the speed of light as your absolute upper limit. Let's talk about some specific destinations that capture our imagination. Kepler 452b, discovered in 2015 by NASA's Kepler Space Telescope, orbits a G-type star similar to our Sun in the constellation Cygnus. It's roughly 60% larger than Earth, orbits within its star's habitable zone, and receives about the same amount of energy from its star as Earth receives from the Sun. Its orbital period is 385 days, remarkably similar to Earth's 365 days. Some scientists have called it Earth's cousin or Earth 2.0. There's just one tiny problem: Kepler 452b is 1,400 light-years away. 1,400 light-years. At 10% light speed, that journey would take 14,000 years. At 1% light speed, 140,000 years. Modern humans have only existed for about 300,000 years. Our entire species hasn't been around twice as long as it would take to reach this potentially habitable world at 1% light speed. The light we see from Kepler 452b today left that star system in the year 626. Muhammad had been dead for only 6 years. The Tang dynasty ruled China. The Maya civilization flourished in Central America. The Byzantine Empire was fighting for survival. Everything that has happened in human history since then, every war, every discovery, every rise and fall of empires, all occurred during the time it took light to travel from that distant star to our telescopes. If we sent a signal to Kepler 452b today, traveling at light speed, it would arrive in the year 3426. If anyone was there to receive it and they immediately responded, we'd get their reply in the year 4826. Nearly 28 centuries from now. This is the tyranny of distance in our universe. This is why the speed of light, despite being the fastest thing in existence, is agonizingly slow on cosmic scales. Now let's consider the question of alien civilizations. The Fermi paradox, named after physicist Enrico Fermi, asks a simple but profound question: if intelligent life is common in the universe, where is everybody? With hundreds of billions of stars in our galaxy alone, many with planetary systems, and billions of years for life to evolve and develop technology, we should expect to see evidence of other civilizations. We should detect their radio signals, their spacecraft, their megastructures. Yet we see nothing. We hear nothing. The universe appears empty of other intelligences. Many solutions to the Fermi paradox have been proposed. Perhaps life is rare. Perhaps intelligence is rare. Perhaps technological civilizations tend to destroy themselves. Perhaps they lose interest in exploration. Perhaps they're hiding. Perhaps they've transcended physical form. Perhaps we're looking in the wrong way or listening on the wrong frequencies. But there's another, simpler explanation that doesn't require any of these speculations. Perhaps the distances are simply too great. Perhaps the speed of light imposes such severe constraints on interstellar travel that civilizations remain isolated on their home worlds or in their home systems, unable to bridge the vast gulfs between stars. Consider an alien civilization on a planet orbiting a star 100 light-years away. They're advanced, much more so than us. They've solved problems we haven't even thought of yet. They have fusion power, artificial intelligence, nanotechnology, biotechnology beyond our imagination. They've detected Earth's atmosphere and found oxygen, a potential biosignature. They want to visit. They build a spacecraft capable of traveling at 20% light speed, far beyond anything we can currently conceive. This represents a mastery of propulsion physics that would seem like magic to us. Even at this incredible speed, the journey to Earth takes 500 years. 5 centuries. Longer than the United States has existed. Longer than the printing press has existed. About as long as it's been since Columbus sailed to the Americas. The crew that arrives would not be the crew that departed, not even close. Either the ship contains a multi-generational crew, with people born, living their entire lives, and dying aboard the vessel, or the travelers are in some form of suspended animation, frozen or slowed to preserve them across the centuries. Let's think about the engineering challenges of such a journey. The spacecraft would need to be entirely self-sufficient for 500 years. Every system would need redundancy upon redundancy. Food production, water recycling, air generation, waste management, all running flawlessly for centuries. Any breakdown, any failure, means death for everyone aboard. There's no rescue, no resupply, no turning back after a certain point. The ship would need shielding against cosmic radiation, those high-energy particles that sleet through space and would slowly kill an unprotected crew. At 20% light speed, even tiny particles of dust become devastating projectiles. A grain of sand, something that would bounce harmlessly off your skin on Earth, hits with the energy of a bomb when you're traveling at 60,000 kilometers per second. The kinetic energy is 1/2 mass times velocity squared, and that velocity term, when it's a significant fraction of light speed, makes even microscopic particles deadly. Recent research by Philip Lubin at UC Santa Barbara, published in 2016, explored the concept of relativistic spacecraft for interstellar travel. His calculations showed that even a spacecraft massing only 1 gram, accelerated to 25% light speed, would need to contend with interstellar hydrogen. Space isn't empty. There's about 1 hydrogen atom per cubic centimeter in the interstellar medium on average. That doesn't sound like much, but at relativistic speeds, those atoms become a form of radiation. They'd erode shielding, damage electronics, and create a constant shower of secondary particles. A larger spacecraft, say 100 tons, the mass of a large truck, traveling at 10% light speed would sweep through about 10 to the power of 18 hydrogen atoms per second. That's a billion atoms every second, each one hitting with enough energy to damage molecular bonds. Over years or centuries, this erosion becomes catastrophic. Then there's the energy requirement. To accelerate even a small spacecraft to a significant fraction of light speed requires enormous energy. Let's do some math. The kinetic energy of an object is 1/2 times mass times velocity squared. For a 1-ton spacecraft, 1,000 kilograms, accelerated to 10% light speed, that's 30,000 kilometers per second or 30 million meters per second. 1/2 times 1,000 kilograms times 30 million meters per second squared equals 4.5 times 10 to the power of 17 joules. That's 450 million billion joules. To put that in perspective, the Hiroshima atomic bomb released about 63 trillion joules. Our spacecraft would need energy equivalent to over 7,000 Hiroshima bombs just to reach 10% light speed, and that's for a tiny 1-ton probe. A spacecraft large enough to carry living beings, with all the life support, shielding, and redundancy needed for a multi-century journey, would mass far more. Thousands of tons at minimum. Maybe tens of thousands of tons. The energy requirements scale with mass. To accelerate 10,000 tons to 10% light speed would require energy equivalent to 70 million Hiroshima bombs. Where does that energy come from? Nuclear fusion, if you could achieve perfect efficiency, could theoretically provide it, but you'd need to carry enormous amounts of fuel, which adds to your mass, which requires more energy, which requires more fuel. It's a vicious cycle. Antimatter offers higher energy density, but we can currently produce only tiny amounts at tremendous cost, and storing it without it annihilating regular matter is a massive challenge. Some proposals suggest using external power sources. The Breakthrough Starshot Initiative, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, proposes using powerful ground-based lasers to propel tiny spacecraft, each weighing only a few grams, to 20% light speed. The laser would push against a thin light sail attached to the craft, accelerating it over a few minutes to relativistic speeds. This concept could potentially send tiny probes to Alpha Centauri in about 20 years flight time, plus 4 years for the signal to return, for a total of 24 years from launch to receiving data. That's within a human lifetime. It's exciting. It's ambitious. But critically, these would be flyby missions. The craft would scream past their target at 20% light speed, gathering data for a few hours at most, then continue onward into deep space forever. No slowing down, no orbiting, definitely no landing. Why no slowing down? Because slowing down requires just as much energy as speeding up. If you accelerate to 20% light speed, you need to expend equivalent energy to decelerate back to zero. That means twice the energy budget, or carrying your deceleration system with you, which adds mass, which requires more acceleration energy. The problem compounds itself. The Breakthrough Starshot probes would be tiny, massing only a few grams, essentially a camera and transmitter on a chip. They couldn't carry passengers. They couldn't carry much scientific equipment. They'd capture some images and measurements during their brief flyby and transmit the data back to Earth, taking 4 years for that signal to arrive. Now, imagine an alien civilization trying to visit Earth. Even with all these challenges solved, even with propulsion technology far beyond ours, they face the same fundamental constraints. They're bound by the same laws of physics. The speed of light limits them just as it limits us. Let's think about what an interstellar journey would actually mean for any civilization attempting it. Imagine you're a member of an advanced alien species that has detected interesting signals or atmospheric signatures from Earth. Your scientists have studied our planet from afar, analyzing the light passing through our atmosphere during transits, if they happen to be positioned edge-on to our solar system. They found oxygen, methane, and other gases that suggest biological activity. They're intrigued. They want to investigate. Your civilization debates the mission. It will cost an enormous fraction of your society's total energy production. It will require resources that could be used for other purposes. The spacecraft will take centuries to build and centuries more to reach its destination. The individuals who initiate the project will be dead long before it succeeds. Their children will be dead. Their grandchildren will be dead. Generations will live and die before the mission bears fruit. Do you commit to this? Do you spend the resources of your entire world, perhaps multiple worlds, for a payoff that no one currently alive will witness? It's a question of civilizational will, of long-term thinking that extends far beyond any individual lifetime or even any cultural epoch. And let's say your civilization decides, yes, we'll do it. You build the ship, you launch it, and centuries pass. During those centuries, your civilization continues to advance. Your technology improves. Your understanding of physics deepens. And then, perhaps 200 years into the 500-year journey, you achieve a breakthrough. You develop a propulsion system that can reach 30% light speed, or 40%, or some other improvement over the original ship. Now you face a dilemma. Do you launch a second, faster ship that will overtake the first one and arrive earlier? Do you radio the first ship to turn around, wasting 2 centuries of travel? Do you let the first ship continue, knowing it will arrive to find a second expedition already there, making the first crew's sacrifice somewhat meaningless? This is called the weight calculation, the question of whether it's ever the right time to launch an interstellar mission when technology keeps improving. Mathematician Andrew Kennedy explored this problem in a 2006 paper. He calculated that if you expect propulsion technology to improve at a predictable rate, there's an optimal time to launch based on when the transit time plus the waiting time is minimized. Launch too early, and a later mission overtakes you. Wait too long, and you unnecessarily delay the mission. The calculation depends on the rate of technological improvement, which is impossible to predict far into the future. For a civilization considering interstellar travel, this creates a form of paralysis. Why launch now when waiting 50 years might give you technology that cuts the travel time in half? But then, why launch in 50 years when waiting another 50 might cut it in half again? You can always justify waiting a bit longer. Yet even with these improvements, you never escape the fundamental constraint. You can approach the speed of light, but you cannot exceed it. You might go from 10% to 20% to 50% to 90% light speed, but that last gap, from 99% to 100%, requires infinite energy. It's asymptotic. You can always get closer but never arrive. At 99% light speed, relativistic effects become extreme. Time dilation means that travelers experience time much more slowly than the rest of the universe. A journey that takes 1,000 years from the perspective of the home planet might take only about 140 years for the travelers. This sounds advantageous, and in some ways it is, but it creates its own problems. When the travelers return, if they return, everyone they knew is dead. The civilization they left has advanced or collapsed or transformed beyond recognition. They're living fossils, anachronisms from a bygone era. The cultural and psychological impacts would be staggering. You'd be an immigrant not just to another place but to another time, unable to ever go home to the world you remember because that world no longer exists. And this assumes the civilization survives. Species go extinct. Civilizations collapse. Earth's history is littered with societies that rose and fell: the Sumerians, the Egyptians, the Maya, the Romans, countless others. We like to think modern technological civilization is different, more resilient, but we're still vulnerable to war, disease, environmental catastrophe, asteroid impacts, and threats we haven't even imagined. A civilization that launches an interstellar mission is making a bet that they'll still exist when the mission returns or even when the mission arrives at its destination. Over timescales of centuries or millennia, that's far from guaranteed. Now let's flip the scenario. Let's imagine an alien civilization has overcome all these obstacles. They've committed the resources, they've built the ship, they've launched it, and centuries later, they arrive in our solar system. What happens next? First, they'd need to decelerate. If they've been traveling at, say, 20% light speed, they can't just slam into Earth orbit. They need to shed all that kinetic energy, which requires energy and time. If they use the same propulsion system that accelerated them, assuming it still works after centuries of dormancy, the deceleration phase takes just as long as the acceleration phase did. If it took 10 years to reach 20% light speed, it takes 10 years to slow back down. During that time, they're vulnerable, unable to maneuver quickly, committed to their trajectory. Once in our solar system, they'd likely observe from a distance first. They wouldn't know what they're walking into. Is Earth inhabited by primitive organisms, multicellular life, intelligent but pre-technological beings, or a spacefaring civilization that might see them as a threat? Depending on when they left their home world and how long the journey took, the Earth they observed from afar might be very different from the Earth they encounter upon arrival. Remember, light takes time to travel. If they're observing Earth from 100 light-years away, they're seeing Earth as it was 100 years ago. They're seeing 1926, a world with early radio technology, automobiles becoming common, no computers, no nuclear weapons, no satellites, no space program. They might decide based on that observation that Earth is safe to approach, that we're primitive and pose no threat. But by the time their ship arrives after a 500-year journey, it's now the year 2426. 500 years have passed. Who knows what Earth would be like then? We might be a peaceful interplanetary or even interstellar species ourselves. We might have destroyed ourselves. We might have created artificial superintelligence. We might have reshaped our solar system with megastructures. The aliens arrive expecting the Earth of 1926 and instead find something completely different. This temporal disconnect is an unavoidable consequence of the speed of light. Information is always outdated. Your decisions are always based on old data. By the time you act on what you've observed, the situation has changed. And here's another layer of complexity: communication. Let's say these aliens arrive in our solar system and want to communicate with their home world. Maybe they want to report their findings, request guidance, or simply send a message that says, "We made it, we're here." That message travels at light speed back to their origin. If they came from 100 light-years away, their message takes 100 years to arrive. If the home civilization replies immediately, that reply takes another 100 years to reach the expedition. A round-trip communication takes 200 years. This means the expedition operates in complete isolation. They make decisions based on guidance that was given 200 years ago, regarding a situation that no longer exists. They can't ask for help. They can't receive updates. They're on their own, separated from their civilization not just by distance but by time itself. Arthur C. Clarke explored this idea in his novel The Songs of Distant Earth, where Earth sends out colony ships to distant stars over centuries. By the time the later ships overtake the earlier ones, the home civilization has changed so much that the different waves of colonists barely recognize each other as coming from the same culture. The speed of light doesn't just make travel slow, it makes coordination impossible over interstellar distances. It fragments any attempt at maintaining a coherent civilization across multiple star systems. Each colony becomes isolated, evolving independently, diverging culturally and perhaps even biologically over sufficient time. Now, some of you might be thinking, what about wormholes? What about warp drives? What about all those science fiction concepts that let us bypass the light speed limit? These are legitimate questions, and they deserve serious answers. Wormholes are theoretical structures predicted by Einstein's general theory of relativity. Also called Einstein-Rosen bridges, they're essentially shortcuts through space-time. Imagine space as a flat sheet of paper. If you want to travel from one point to another, normally you'd travel across the surface. But if you could fold the paper so the 2 points touch, then poke a hole through both layers, you'd have a tunnel connecting them, a wormhole. You could travel through the tunnel and arrive at your destination much faster than traveling across the surface. Mathematically, wormholes are allowed by general relativity. The equations don't forbid them. But there are enormous problems with making them real. First, naturally occurring wormholes, if they exist at all, would be microscopic and unstable, forming and collapsing in tiny fractions of a second. To make a wormhole large enough for a spacecraft or a human to pass through, and to keep it open long enough to traverse, you'd need what physicists call exotic matter, a form of matter with negative energy density. This is matter that has less than zero energy, which sounds absurd because how can something have less than nothing? Exotic matter has never been observed. Some quantum effects, like the Casimir effect discovered in 1948, involve negative energy densities in specific configurations, but these are tiny, localized effects. Scaling them up to wormhole size would require amounts of exotic matter that we have no idea how to produce or even if such production is possible. Second, even if you could create and stabilize a wormhole, you can't use it to travel to somewhere you haven't already been. Think of it this way, to create a wormhole connecting Earth to a star 100 light-years away, you'd first need to transport one end of the wormhole to that star. But transporting it there requires traveling there, and you're still limited by the speed of light. So the first trip still takes at least 100 years. The wormhole might allow quick travel afterward, but establishing the wormhole network requires slow, conventional travel first. Physicist Kip Thorne, who won the Nobel Prize in 2017 for his work on gravitational waves, has written extensively about wormholes. He consulted on the movie Interstellar to ensure the depiction of the wormhole was as scientifically accurate as possible. But even Thorne emphasizes that while wormholes are theoretically possible, we have no idea if they can actually exist, and we certainly don't know how to create or control them. Then there's the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. This concept involves contracting space in front of a spacecraft and expanding space behind it, creating a bubble of normal spacetime that moves faster than light even though nothing inside the bubble breaks the light speed limit locally. The ship doesn't move through space, space moves around the ship. It's a brilliant idea that respects the laws of relativity while still achieving faster than light travel. But, and this is a massive but, the Alcubierre drive also requires exotic matter with negative energy density. Depending on the configuration, the original calculation suggested you'd need an amount of negative energy equivalent to the mass energy of Jupiter, the largest planet in our solar system. Later refinements by Harold White at NASA reduced this to perhaps the mass energy of the Voyager spacecraft, about 700 kilograms, but that's still 700 kilograms of exotic matter that we don't know how to make. Additionally, the Alcubierre drive has some disturbing side effects. Research published in 2012 by researchers in Australia showed that as the warp bubble travels, it accumulates particles and radiation at its forward edge. When the drive shuts off and the bubble collapses, this accumulated matter and energy releases in a devastating burst that would sterilize anything in front of the ship. Your arrival at the destination would be preceded by a blast of high-energy particles that would destroy whatever you came to visit. There are also causality problems. Both wormholes and warp drives potentially allow time travel to the past, which creates paradoxes. If you can travel faster than light in one reference frame, relativity says there's another reference frame in which you're traveling backward in time. This leads to situations where you could theoretically arrive before you left, creating logical inconsistencies that physics doesn't know how to resolve. Stephen Hawking proposed the chronology protection conjecture, essentially a law of physics that prevents time travel to the past and thus prevents the paradoxes it would create. If this conjecture is correct, then any mechanism that allows faster-than-light travel must be prohibited by some physical law we haven't fully understood yet. The bottom line is this: while exotic propulsion concepts are fun to think about and physicists should absolutely continue exploring them, we have no evidence they're actually possible, and significant theoretical reasons to think they might not be. Banking on wormholes or warp drives to solve the interstellar travel problem is like banking on magic. Maybe it exists, but you shouldn't base your plans on it. So we return to the fundamental constraint: the speed of light is slow on cosmic scales, and we can't exceed it. Let's think about the implications for the search for extraterrestrial intelligence, what we call SETI. Since 1960, when astronomer Frank Drake conducted the first radio search for alien signals, we've been listening to the cosmos. We've scanned thousands of stars across multiple frequencies, looking for any indication of artificial signals, any pattern that couldn't be produced by natural processes. We found nothing. Silence. The universe appears empty. The Allen Telescope Array in California, the Green Bank Telescope in West Virginia, the Arecibo Observatory before its collapse in 2020, and other facilities around the world have devoted thousands of hours to listening. The Breakthrough Listen initiative, launched in 2015 with $100 million in funding, represents the most comprehensive search ever undertaken. It's surveying the 1 million nearest stars, the center of our galaxy, and the 100 nearest galaxies across a wide range of radio and optical frequencies. Still nothing. No confirmed signals. A few false alarms, like the famous WOW signal detected in 1977, which was a strong narrowband radio signal that lasted 72 seconds and never repeated. Despite its intriguing properties, we don't know what caused it, and it's never been detected again. Most likely it was an artifact, perhaps from Earth-based interference, rather than an alien transmission. The silence is deafening, and the speed of light offers one possible explanation. If technological civilizations are separated by hundreds or thousands of light years, they're effectively isolated. Even if they're broadcasting powerful signals, those signals weaken with distance according to the inverse square law. By the time a signal has traveled 100 light years, it's been diluted across a sphere 100 light years in radius. The signal strength decreases as 1 over the distance squared. Our own radio signals have been leaking into space since we invented radio in the late 19th century. The first radio transmissions date to about 1895 with Guglielmo Marconi's experiments. More powerful transmissions began in the 1920s and 30s with commercial radio broadcasts. Television signals started in the 1940s. All of these signals travel outward at light speed, creating an expanding bubble of electromagnetic noise centered on Earth. That bubble is now about 130 light years in radius, as of 2026. Any alien civilization within that bubble, with a sensitive enough receiver aimed at our solar system at the right time, could potentially detect our presence. Beyond that bubble, we're invisible, our signals haven't reached them yet. But here's the thing, our radio signals are weak. They're not intentionally beamed at the stars. They leak into space as a side effect of broadcasting to each other. A civilization 100 light-years away would need a radio telescope far larger than anything we've built to detect our leaked signals. They'd need to know where to look, when to look, and what frequencies to monitor. Finding Earth's faint radio whisper among the cacophony of natural cosmic radio sources would be like hearing a whisper in a hurricane. We've sent a few intentional messages to the stars. The Arecibo message, transmitted in 1974 toward the globular cluster Messier 13, was a 3-minute broadcast containing information about humans, DNA, our solar system, and the Arecibo telescope itself. Messier 13 is 25,000 light-years away, so the message won't arrive until the year 26,974. If anyone receives it and responds immediately, we'd get the reply in the year 51,974. That's nearly 50,000 years from now. Other messages have been sent to closer targets. In 2008, NASA beamed the Beatles' song Across the Universe toward Polaris, the North Star, which is about 433 light-years away. A lovely symbolic gesture, but Polaris won't receive it until the year 2441, and a response wouldn't arrive until the year 2874. These timescales are absurd from a human perspective. They're longer than recorded history. They're longer than agriculture. They're approaching the length of time that anatomically modern humans have existed. And this brings us to a crucial realization: interstellar communication, let alone interstellar travel, requires a kind of patience that may be fundamentally incompatible with the way biological civilizations work. We're evolved for immediate gratification, for problems and solutions on timescales of seconds, hours, days, maybe years. Waiting centuries or millennia for responses to messages goes against every instinct we have. Perhaps truly advanced civilizations develop this patience, extending their perspective across thousands or millions of years. Or perhaps they don't. Perhaps the transition to thinking on such long timescales is so difficult that most civilizations never make it. They remain bound to their home worlds not because they lack technology but because they lack the cultural and psychological framework to commit to projects spanning hundreds of generations. There's another possibility that's worth considering: maybe advanced civilizations don't travel or communicate across interstellar distances because they don't need to. Everything they could want, every resource, every environment, can be created in their home solar system. Think about our own solar system. We have 8 planets, dozens of moons, millions of asteroids, and vast amounts of raw material. The asteroid belt alone contains enough metal and minerals to build habitats for trillions of people. The Sun provides essentially unlimited energy for the next 5 billion years. With sufficiently advanced technology, we could create rotating habitats, O'Neill cylinders named after physicist Gerard O'Neill, who proposed them in 1976, providing comfortable living space with artificial gravity. These habitats could be customized to any environment you can imagine. Want to live in a tropical paradise? Done. Prefer Arctic tundra? No problem. Want to experience conditions nothing like Earth? Create whatever you want. You could have millions of distinct habitats, each one a world unto itself, all within a few light hours of each other. Communication would be essentially instantaneous compared to interstellar timescales. Travel between habitats would take days or weeks, not centuries. From this perspective, leaving your solar system makes little sense. Why spend centuries traveling to another star when you can create any environment you want at home? The only reason to go would be curiosity, scientific exploration, or the desire to meet other life forms. Those are valid motivations, but they might not be sufficient to justify the enormous costs and risks. This could explain the Fermi paradox. Advanced civilizations might be common, but they're staying home, building elaborate civilizations within their own solar systems, having no particular reason to venture into the vast darkness between stars. They might send out probes, small automated scouts like our Voyagers, crawling slowly toward nearby stars. But mounting crewed expeditions, or even just communicating regularly, might simply not be worth the effort. There's a concept in astrobiology and SETI research called the Great Filter. The idea, proposed by economist Robin Hanson in 1996, suggests that there must be some incredibly difficult step in the evolution from simple chemistry to spacefaring civilization. This filter could be in our past, perhaps the origin of life itself is extraordinarily rare, or the evolution of complex cells, or the development of intelligence. If the filter is behind us, we're lucky to have passed it, and we might be alone or nearly alone in the galaxy. But the filter could also be in our future. Perhaps there's a stage that most civilizations reach and then fail to pass. Nuclear war, environmental collapse, resource depletion, artificial intelligence gone wrong, synthetic biology disasters. There are many ways a technological civilization could destroy itself. If this is the case, the galaxy might be full of ruins, dead civilizations that reached our level or beyond and then collapsed. The speed of light could itself be part of the Great Filter. Perhaps the inability to exceed light speed means that civilizations remain forever isolated, unable to spread, unable to ensure their survival by becoming multisystem species. A single catastrophe, an asteroid impact, a gamma-ray burst, a supernova, could wipe out a civilization confined to one solar system. Without the ability to spread to other stars quickly, civilizations remain vulnerable. But if spreading to other stars takes centuries or millennia per star, and if civilizations typically last only thousands of years before collapsing or transforming into something unrecognizable, then maybe interstellar colonization never happens. The timescales don't line up. By the time your colony ship reaches another star, your home civilization might not exist anymore. We can look at our own history for perspective. 5,000 years ago, the Sumerians were inventing writing. Egyptian civilization was emerging. These seemed permanent, eternal. Yet they fell. Their languages are dead, their gods forgotten except as historical curiosities. What makes us think our civilization will last longer? What makes us think we'll maintain continuity across the timescales needed for interstellar travel? And yet, despite all these challenges, despite the crushing distances and the aching slowness of light, despite the energies required and the time involved, I don't think we should conclude that interstellar travel is impossible or that we'll never encounter other civilizations. Difficult? Yes. Expensive? Absolutely. Requiring patience and long-term thinking beyond anything our species has demonstrated. Without question. But impossible? That's harder to say. Human beings have accomplished extraordinary things when we've committed to them. We've split the atom, eradicated diseases, landed on the moon, built machines that can think. We've decoded our own genome, imaged black holes, and detected gravitational waves rippling through space-time from collisions billions of light-years away. What we lack in physical capability, we sometimes make up for in cleverness, determination, and stubbornness. There are strategies we could pursue, even with current or near-future technology, that make interstellar travel more feasible. None of them violate physics. None of them require exotic matter or speculative breakthroughs. They're just hard, expensive, and require thinking on timescales longer than any nation or corporation typically plans for. One approach is the Generation Ship, a massive spacecraft designed to support a self-sustaining human population for centuries or millennia. The ship would be essentially a mobile habitat, a small piece of Earth traveling through space. Hundreds or thousands of people would live aboard, farming, manufacturing, recycling, maintaining systems, having children, and passing the mission down through generations. The original crew would know they'd never see the destination. Their children wouldn't either. Nor would their grandchildren. The arrival would be experienced by descendants so far removed from the original crew that they might barely remember Earth except as a historical abstraction, a place their ancestors came from long ago. The British Interplanetary Society conducted a detailed study of this concept in the 1970s called Project Daedalus. They designed an unmanned probe, not a generation ship, but their work established the basics of what interstellar propulsion with nuclear pulse propulsion might look like. A later redesign called Project Icarus, started in 2009, updated the concept with more modern assumptions. For a crewed generation ship, you'd need a closed-loop life support system that recycles everything, water, air, waste, with essentially perfect efficiency. Any loss, even a tiny percentage per year, compounds over centuries and eventually leads to shortages. You'd need robust food production, probably through agriculture and aquaculture. You'd need manufacturing capability to repair and replace parts. You'd need medical facilities to handle injuries and illnesses. You'd need entertainment, education, social structures, governance systems that remain stable over multiple generations. The psychological and sociological challenges might be even harder than the engineering ones. How do you maintain morale and purpose when the mission won't be completed in your lifetime or your children's lifetimes or their children's lifetimes? How do you prevent social breakdown, revolution, or the emergence of a dictatorship when the population is sealed in a can they can never leave? How do you preserve knowledge and skills across generations when direct experience is limited to life aboard the ship? Science fiction has explored these questions extensively. Arthur C. Clarke's Rendezvous with Rama, Robert Heinlein's Universe, Paul Anderson's Tau Zero, Kim Stanley Robinson's Aurora, and many others imagine generation ships and the societies that might develop aboard them. These stories often depict social collapse, loss of purpose, and populations that forget they're on a ship, thinking it's the entire universe. These aren't just entertaining plots. They're genuine concerns. A generation ship would be conducting a multi-century social experiment with no control group, no backup plan, and no possibility of rescue if things go wrong. The stakes couldn't be higher. An alternative to keeping people awake for centuries is suspended animation or hibernation. If we could safely put people into a state of drastically slowed metabolism, they could sleep through the journey and wake up at the destination. Animals do this naturally. Bears hibernate. Some frogs freeze solid in winter and thaw out in spring. Certain tardigrades, microscopic creatures, can enter a state called cryptobiosis where their metabolism drops to nearly zero, and they can survive for decades in this state. We've made progress toward this for humans. Therapeutic hypothermia is already used in medicine to slow metabolism and preserve brain function during cardiac arrest or surgery. Patients have been cooled to temperatures as low as 10 degrees Celsius, kept in that state for hours, and successfully revived. But extending this to weeks, months, or years introduces new problems. Long-term suspended animation would require preventing ice crystal formation in cells, which causes damage. Cryoprotectants, chemicals that prevent freezing, are used in existing cryonics procedures, but current techniques cause toxicity over time. Successfully reviving someone frozen for years or centuries remains beyond our capability, though research continues. SpaceWorks Enterprises, an aerospace company, has studied torpor-inducing transfer habitats for NASA. Their concept involves cooling astronauts to reduce their metabolic rate by 50 to 70%, keeping them in a therapeutic torpor for weeks or months. This isn't true suspended animation, but it's a step toward it. If perfected, it could reduce the consumables needed for long missions, shrink habitat size, and perhaps extend crew psychological endurance. But even if we solve suspended animation, the ship still needs to function for centuries. The life support for sleeping passengers is simpler than for waking ones, but propulsion, navigation, communication, and revival systems must all work flawlessly after decades or centuries of inactivity. Any failure means the crew never wakes up, or wakes up to a dying ship, or misses the destination and continues onward forever. Another approach is to not send biological humans at all, but rather to send the information needed to create humans at the destination. This is sometimes called a seed ship or a genesis ship. The spacecraft would carry frozen embryos or even just digital information encoding human DNA and instructions for growing and raising humans. Upon arrival, automated systems would establish infrastructure, then create and raise a new generation of humans who would be native to the destination world. This sounds like science fiction, and it is, but the underlying technologies aren't entirely speculative. We can already freeze embryos and store them for years. In vitro fertilization is routine. Artificial wombs are being developed for medical purposes, currently capable of gestating premature lambs. Extending this to human gestation from conception to birth is ethically complex but probably technically feasible. The hard part is raising the children. Humans require years of intensive care and education. We're not like sea turtles that hatch and immediately know how to survive. We need teaching, socialization, culture transmission. How do you program an AI to be a good parent? How do you ensure the children grow up psychologically healthy without human role models? What kind of society would emerge from this scenario? These questions touch on philosophy and ethics as much as engineering. Are humans created this way truly the continuation of Earth's civilization, or are they something new, only tenuously connected to their origin? Would it be ethical to create human children in such circumstances, essentially orphans on an alien world? Different people will answer these questions differently. Perhaps the most realistic near-term approach to interstellar exploration isn't sending humans at all, but sending machines. Robotic probes don't need life support, don't get bored, don't suffer psychological distress, and can be much smaller and lighter than crewed vehicles. They can also accept higher risks. If a probe fails, it's a scientific and economic loss, but no lives are lost. The Voyager probes, launched in 1977, are our first interstellar spacecraft, though they weren't designed for interstellar missions. They were sent to explore the outer planets, which they did magnificently, but after completing those encounters, they continued outward. Voyager 1 crossed the heliopause, the boundary where the Sun's influence ends and interstellar space begins, in 2012. It's now over 15 billion miles from Earth, about 21 light-hours away. Voyager 1 is traveling at about 38,000 miles per hour, which sounds fast until you realize that's only 0.006% the speed of light. At this rate, it would take about 73,000 years to travel 1 light-year. The nearest star, Proxima Centauri at 4.24 light-years, would take roughly 310,000 years to reach at Voyager's speed. Modern humans haven't existed that long. But Voyager wasn't designed for interstellar travel. It's just coasting on the momentum from its 1970s launch and gravity assists from the outer planets. A dedicated interstellar probe could do much better. The Breakthrough Starshot project, announced in 2016, proposes sending tiny spacecraft to Proxima Centauri within a human lifetime. The concept is audacious: build thousands of miniature probes, each weighing only a few grams and carrying cameras, sensors, and communication equipment. Attach each probe to a lightweight reflective sail. Then use an enormous ground-based laser array to blast these sails with intense light for several minutes, accelerating the probes to 20% the speed of light. At that speed, the probes would reach Proxima Centauri in about 20 years. They'd fly through the system, gathering data and images, and transmit their findings back to Earth. The transmission would take another 4.2 years to arrive, so the total mission time from launch to receiving data would be about 25 years. That's within a human career span. Scientists who design the mission could potentially see the results before they retire. The challenges are immense but not obviously impossible. The laser array would need to generate about 100 gigawatts of power focused into a beam approximately 6 miles in diameter. That's roughly the output of 100 large nuclear power plants, operated for just a few minutes per launch. The beam would need to track the tiny sail with extreme precision as it accelerates away from Earth. The sail itself would need to be incredibly thin and lightweight, yet strong enough to withstand the intense radiation pressure without tearing or vaporizing. The probe would need to survive 20 years in interstellar space, enduring cosmic rays, dust impacts, and extreme cold, then function perfectly during a brief flyby lasting only hours. It would need to capture images and data, then turn its antenna toward Earth, for 0.2 light-years away, and transmit with enough power that our telescopes can detect the signal. Each of these challenges is at the edge of our current technology or slightly beyond, but nothing requires new physics. It's an engineering problem, albeit an extraordinarily difficult one. The Breakthrough Starshot Initiative has funding, a team of respected scientists and engineers, and is conducting research into the various components. Stephen Hawking, before his death in 2018, was a strong supporter of Breakthrough Starshot. He understood that while faster-than-light travel might be impossible, 20% light speed is achievable with sufficient commitment. He recognized that our species' long-term survival might depend on becoming interstellar, and that we need to start working toward that goal now, even if completion is decades away. But let's be realistic about the limitations. Even if Breakthrough Starshot succeeds perfectly, it's a flyby mission. The probes would scream through the Proxima Centauri system at 60 million miles per hour, too fast to stop or orbit. They'd get a few hours, maybe days if they're lucky, to observe and photograph whatever is there. Then they'd continue into the darkness beyond, their mission complete, traveling forever into the void. To actually explore a star system properly, to orbit planets, land on surfaces, analyze atmospheres, search for life, you need to slow down. And slowing down requires energy, lots of it, roughly equal to the energy it took to speed up in the first place. For a laser-pushed sail, there's no laser at the destination to slow you down. You'd need a different deceleration method. One concept is a magnetic sail or mag-sail, proposed by physicist Robert Zubrin. As the probe approaches the destination star, it deploys a large loop of superconducting wire, creating a magnetic field. This field interacts with the charged particles in the stellar wind, creating drag that gradually slows the probe. It's like deploying a parachute, but the parachute catches charged particles instead of air molecules. The problem is that stellar winds are tenuous. Slowing down takes a long time and requires approaching relatively close to the star. You'd need to aim your trajectory carefully to pass through the region where the stellar wind is dense enough to be effective but not so close that radiation fries your electronics. And the superconducting loop would need to be enormous, miles in diameter, yet incredibly lightweight and deployable from a tiny probe. Another idea is to carry your own fuel for deceleration, but that brings us back to the tyranny of the rocket equation. If you need to decelerate from 20% light speed, you need a huge amount of fuel. Carrying that fuel means you need even more energy to accelerate it in the first place. The mass ratios become prohibitive very quickly. The reality is that with current physics, fast interstellar flyby missions are difficult but possible. Stopping at the destination is much, much harder. Sending humans is harder still. And doing any of this on timescales shorter than decades or centuries requires technological capabilities we don't yet have. So where does this leave us in our search for alien civilizations and our assessment of whether they might visit Earth? If aliens exist, and if they're aware of us, they face exactly the same constraints we do. They can't exceed the speed of light. They need enormous energy for interstellar travel. They experience time dilation if they travel fast enough, but only from their perspective. The rest of the universe still ages normally. They need to decelerate when they arrive. They need to communicate across light-year distances with corresponding delays. An alien civilization 100 light-years away observing Earth sees our past. If they're watching us right now in 2026, they're seeing Earth as it was in 1926. They see early radio technology, no computers, no satellites, no nuclear technology, no space program. Based on that observation, they might decide we're an interesting but primitive species worth visiting. So they mount an expedition. Let's say their technology is more advanced than ours, and they can travel at 30% light speed, faster than the 20% breakthrough Starshot aims for. The journey takes about 333 years from our perspective, though less time passes for the travelers due to time dilation. They launch in 1926 as observed from Earth, but remember, they're 100 light-years away, so their actual launch year in their own time frame would be around 1826. The information about Earth from 1926 takes 100 years to reach them, so they observe it and decide to launch in 1926 in Earth time, but the light showing them 1926 Earth is just arriving. Actually, let me recalculate this more carefully, because the relativistic timing gets confusing. Let's set up a scenario more clearly. Suppose there's an alien civilization 100 light-years from Earth. In the year 1926 on Earth, we start broadcasting radio signals. That light, carrying information about 1926 Earth, travels outward at light speed and reaches the alien civilization in the year 2026 by Earth's calendar, 100 years later. The aliens receive these signals, analyze them, and decide to visit. They immediately launch a spacecraft traveling at 30% light speed toward Earth. The journey distance is 100 light-years, but they're traveling at 30% light speed, so from Earth's reference frame, the journey takes 100 divided by 0.3, which equals 333 years. They launched in 2026 Earth time and arrive in 2359. But from their own perspective, time dilation means less time passes for them. At 30% light speed, the Lorentz factor is about 1.05, so they experience roughly 318 years of travel time rather than 333. Still a very long journey by any standard. When they arrive in 2359, they encounter an Earth that is 433 years more advanced than the one they observed. They saw 1926, they arrive in 2359. Humans might be a vastly different species by then. We might be extinct. We might be a galaxy-spanning civilization. We might have uploaded our consciousness into machines. We might have destroyed ourselves and the planet could be a radioactive wasteland. They have no way of knowing until they arrive. This fundamental uncertainty is inherent in all interstellar travel at sublight speeds. You commit resources to a mission based on centuries-old information, and you arrive to face whatever reality has emerged in the meantime. This temporal disconnect has profound implications for any hypothetical alien visitation of Earth. If UFO reports represent actual alien spacecraft, and I want to be very clear that there's no compelling evidence that they do, but if they did, those aliens would have needed to decide to come here based on observations of Earth from decades, centuries, or millennia ago, depending on their distance from us. If they're from a star system 10 light-years away, they're seeing Earth as it was 10 years ago. They'd see our 2016 technology level, our politics, our environmental state. If they decided to come and traveled at a significant fraction of light speed, they might arrive within a few decades of their decision. That's somewhat reasonable. But if they're from 100 light-years away, they're seeing 1926 Earth. If they're from 1,000 light-years away, they're seeing Earth from the year 1026, the medieval period. There were no radio signals then, no industrial activity, nothing to distinguish Earth from billions of other planets except possibly spectroscopic signatures of oxygen and other biosignatures in the atmosphere. For a civilization to detect those biosignatures, decide Earth is interesting, and travel here would take a minimum of 1,000 years for the light to reach them, then however long the journey takes. At 10% light speed, the journey takes 10,000 years. At 50% light speed, 2,000 years. Either way, they committed to visiting a planet showing medieval characteristics and would arrive at the modern or future Earth. Would they do that? Would any civilization commit enormous resources to visiting a planet based on 1,000-year-old information showing no technology? maybe for scientific purposes, maybe they're cataloging life-bearing worlds, but it seems like a tremendous investment for uncertain returns. The more I think about this, the more I suspect that if intelligent aliens exist, and if they're traveling between stars at all, they're probably doing what we would do, sending small, fast probes rather than large, crude vessels. Probes are cheaper, lower risk, and can be sent in large numbers to many destinations. A civilization might seed the galaxy with millions of self-replicating probes that travel from star to star, gathering data and reporting back. This idea was proposed by mathematician John von Neumann in the 1940s. He envisioned self-replicating machines that could be sent to other star systems, where they'd gather resources, build copies of themselves, and send those copies to yet more star systems. Eventually, these von Neumann probes would spread throughout the galaxy, exploring every star system and reporting their findings back to their creators. The mathematics of exponential growth means that even at slow speeds, von Neumann probes could explore the entire Milky Way galaxy in a few million years. If the probes travel at 1% light speed and spend 1,000 years in each system gathering resources and replicating before sending copies to new systems, the wave of probes expands outward. Each probe produces multiple copies, so the number increases exponentially. Within a few million years, every star system in the galaxy would have been visited. This timeline is short compared to the age of the galaxy, about 13.6 billion years, or even the age of our solar system, for 0.6 billion years. If any civilization anywhere in the galaxy had launched von Neumann probes even just a few million years ago, the probes should be everywhere by now, including our solar system. Yet we see no evidence of them. This is sometimes called the von Neumann probe paradox or the Berserker scenario, after the Fred Saberhagen science fiction stories about self-replicating killing machines. If such probes existed, where are they? Why haven't we found one in our asteroid belt or on the Moon or orbiting Jupiter? Maybe they're here and we haven't recognized them. Maybe they're small and stealthy. Maybe they're waiting, observing us, reporting back. This is the zoo hypothesis, proposed by astronomer John Ball in 1973, suggesting that aliens know about us but are deliberately not making contact, treating Earth like a zoo or nature preserve, a protected area where we're allowed to develop without interference. It's an interesting idea, but it requires a level of coordination and restraint that seems implausible for a galactic civilization. Even if most aliens agree to leave us alone, it only takes one group that doesn't care about the rules to make contact. Unless there's some kind of galactic government enforcing non-interference, which seems like a big assumption, you'd expect at least some contact or interference. The simplest explanation for why we don't see alien probes is that they don't exist, either because aliens are extremely rare, or because even they find interstellar travel too difficult or too pointless to bother with. And this brings me back to my central thesis: the speed of light is catastrophically slow for interstellar travel. It's the universe's speed limit, and it creates barriers that may be fundamentally insurmountable for biological civilizations operating on biological timescales. Maybe the universe is full of civilizations, but they're all stuck in their home solar systems, unable or unwilling to make the journey to other stars. Maybe they communicate using radio or laser signals, conversations where each exchange takes centuries. Maybe they share information, science, art, philosophy, but never meet face to face because meeting requires commitment across timescales that no culture can maintain. Or maybe the transition to interstellar civilization requires a fundamental transformation. Maybe you need to become something other than biological organisms with lifespans measured in decades. Maybe you need to upload consciousness into machines that can wait millennia without boredom or degradation. Maybe you need to abandon individuality entirely and become a collective intelligence that operates on cosmic timescales. If this transformation is necessary, it might explain the Great Filter. Maybe most civilizations never make this transition. They reach a technological level like ours or somewhat beyond, then plateau, either because they destroy themselves or because they can't or won't take the next step. The galaxy could be full of civilizations, all stuck at roughly our level, all staring out at the stars and wondering why the universe seems so empty. There's a melancholy to this vision. We might be surrounded by siblings, other technological species scattered across the galaxy, all of us capable of looking outward, all of us dreaming of contact, but none of us able to bridge the vast distances that separate us. We're like people on distant islands, able to see smoke from each other's fires, able to flash signals across the water, but never able to cross the ocean that divides us. Yet even in this scenario, there's hope. Communication doesn't require physical travel. Radio waves travel at light speed, faster than anything material can go. We can have conversations, albeit very slow ones. A civilization 100 light-years away could send us a message today, and we'd receive it in the year 2126. If we responded immediately, they'd get our reply in 2226, 200 years round trip for a single exchange. That sounds impossibly slow, and by human standards it is. But it's not nothing. Information can be exchanged. Knowledge can be shared. A galaxy-wide conversation could emerge, a vast network of civilizations exchanging data, science, art, and philosophy, even if no two civilizations ever meet in person. We've already started this process. In 1974, we sent the Arecibo message. We've since sent additional messages, though not many. The Project METI, Messaging to Extraterrestrial Intelligence, advocates for more active transmission to the stars. Critics worry that announcing our presence might be dangerous, that hostile aliens might decide to attack or invade us. Personally, I think the danger is minimal for exactly the reasons I've been discussing. If hostile aliens exist 100 light-years away, they can't hurt us without mounting an expedition that takes centuries. By the time they arrive, we'd have centuries of warning from their response to our message. We'd know they were coming. And what would they gain by attacking? Resources? Every star system has resources. Living space? Building habitats in their home system is easier than traveling centuries to invade ours. Slaves? Any species with interstellar travel capability doesn't need slaves, they have automation. This temporal disconnect has profound implications for any hypothetical alien visitation of Earth. If UFO reports represent actual alien spacecraft, and I want to be very clear that there's no compelling evidence that they do, but if they did, those aliens would have needed to decide to come here based on observations of Earth from decades, centuries, or millennia ago, depending on their distance from us. If they're from a star system 10 light-years away, they're seeing Earth as it was 10 years ago. They'd see our 2016 technology level, our politics, our environmental state. If they decided to come and traveled at a significant fraction of light speed, they might arrive within a few decades of their decision. That's somewhat reasonable. But if they're from 100 light-years away, they're seeing 1926 Earth. If they're from 1,000 light-years away, they're seeing Earth from the year 1026, the medieval period. There were no radio signals then, no industrial activity, nothing to distinguish Earth from billions of other planets except possibly spectroscopic signatures of oxygen and other biosignatures in the atmosphere. For a civilization to detect those biosignatures, decide Earth is interesting, and travel here would take a minimum of 1,000 years for the light to reach them, then however long the journey takes. At 10% light speed, the journey takes 10,000 years. At 50% light speed, 2,000 years. Either way, they committed to visiting a planet showing medieval characteristics and would arrive at the modern or future Earth. Would they do that? Would any civilization commit enormous resources to visiting a planet based on 1,000-year-old information showing no technology? Maybe for scientific purposes, maybe they're cataloging life-bearing worlds, but it seems like a tremendous investment for uncertain returns. The more I think about this, the more I suspect that if intelligent aliens exist, and if they're traveling between stars at all, they're probably doing what we would do, sending small, fast probes rather than large, crude vessels. Probes are cheaper, lower risk, and can be sent in large numbers to many destinations. A civilization might seed the galaxy with millions of self-replicating probes that travel from star to star, gathering data and reporting back. This idea was proposed by mathematician John von Neumann in the 1940s. He envisioned self-replicating machines that could be sent to other star systems, where they'd gather resources, build copies of themselves, and send those copies to yet more star systems. Eventually, these von Neumann probes would spread throughout the galaxy, exploring every star system and reporting their findings back to their creators. The mathematics of exponential growth means that even at slow speeds, von Neumann probes could explore the entire Milky Way galaxy in a few million years. If the probes travel at 1% light speed and spend 1,000 years in each system gathering resources and replicating before sending copies to new systems, the wave of probes expands outward. Each probe produces multiple copies, so the number increases exponentially. Within a few million years, every star system in the galaxy would have been visited. This timeline is short compared to the age of the galaxy, about 13.6 billion years, or even the age of our solar system, 4.6 billion years. If any civilization anywhere in the galaxy had launched von Neumann probes even just a few million years ago, the probes should be everywhere by now, including our solar system. Yet we see no evidence of them. This is sometimes called the von Neumann probe paradox or the Berserker scenario, after the Fred Saberhagen science fiction stories about self-replicating killing machines. If such probes existed, where are they? Why haven't we found one in our asteroid belt or on the Moon or orbiting Jupiter? Maybe they're here and we haven't recognized them. Maybe they're small and stealthy. Maybe they're waiting, observing us, reporting back. This is the zoo hypothesis, proposed by astronomer John Ball in 1973, suggesting that aliens know about us but are deliberately not making contact, treating Earth like a zoo or nature preserve, a protected area where we're allowed to develop without interference. It's an interesting idea, but it requires a level of coordination and restraint that seems implausible for a galactic civilization. Even if most aliens agree to leave us alone, it only takes one group that doesn't care about the rules to make contact. Unless there's some kind of galactic government enforcing non-interference, which seems like a big assumption, you'd expect at least some contact or interference. Another variation is this dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin in his Remembrance of Earth's Past trilogy. The idea is that the galaxy is full of civilizations, but they all remain silent and hidden because announcing your presence is dangerous. Any civilization that reveals itself risks being destroyed by others who view all unknown civilizations as potential threats. So everyone stays quiet, listening but not transmitting, hiding in the darkness of space like hunters in a dark forest. It's a chilling scenario, and it makes for compelling fiction, but I'm skeptical it reflects reality. The hypothesis assumes that interstellar warfare is feasible and that destruction is easier than communication. But given the difficulties of interstellar travel and the enormous energy requirements, I suspect that any civilization capable of mounting an interstellar attack is also capable of defending against one, creating a mutual deterrence. Moreover, the light speed delay makes warfare strategically bizarre. You can't respond to threats in real time when information and weapons both take years or centuries to cross the battlefield. The simplest explanation for why we don't see alien probes is that they don't exist, either because aliens are extremely rare, or because even they find interstellar travel too difficult or too pointless to bother with. Perhaps intelligent life arises so infrequently that the average distance between technological civilizations is tens of thousands of light-years, making contact effectively impossible even with the most optimistic assumptions about longevity and travel speed. Or perhaps intelligence is common but short-lived. Maybe technological civilizations last only a few centuries on average before destroying themselves through nuclear war, environmental collapse, artificial intelligence disasters, or some other catastrophe we haven't imagined yet. If the typical lifespan of a technological civilization is only 500 years, and it takes thousands of years to mount interstellar expeditions, then the galaxy could be full of ruins, former civilizations that rose and fell before they could reach the stars. This is the great filter hypothesis applied to longevity rather than emergence. Maybe the hard step isn't developing intelligence but sustaining it long enough to become truly interstellar. We're only about 100 years into our technological phase, barely past the threshold where we could destroy ourselves with nuclear weapons, still struggling with climate change, environmental degradation, and the social disruptions caused by rapid technological advancement. Will we make it another 100 years? Another 1,000? It's genuinely uncertain. And this brings me back to my central thesis: the speed of light is catastrophically slow for interstellar travel. It's the universe's speed limit, and it creates barriers that may be fundamentally insurmountable for biological civilizations operating on biological timescales. Maybe the universe is full of civilizations, but they're all stuck in their home solar systems, unable or unwilling to make the journey to other stars. Maybe they communicate using radio or laser signals, conversations where each exchange takes centuries. Maybe they share information, science, art, philosophy, but never meet face to face because meeting requires commitment across timescales that no culture can maintain. Or maybe the transition to interstellar civilization requires a fundamental transformation. Maybe you need to become something other than biological organisms with lifespans measured in decades. Maybe you need to upload consciousness into machines that can wait millennia without boredom or degradation. Maybe you need to abandon individuality entirely and become a collective intelligence that operates on cosmic timescales. If this transformation is necessary, it might explain the great filter. Maybe most civilizations never make this transition. They reach a technological level like ours or somewhat beyond, then plateau, either because they destroy themselves or because they can't or won't take the next step. The galaxy could be full of civilizations, all stuck at roughly our level, all staring out at the stars and wondering why the universe seems so empty. There's a melancholy to this vision. We might be surrounded by siblings, other technological species scattered across the galaxy, all of us capable of looking outward, all of us dreaming of contact, but none of us able to bridge the vast distances that separate us. We're like people on distant islands, able to see smoke from each other's fires, able to flash signals across the water, but never able to cross the ocean that divides us. Yet even in this scenario of isolation, there's hope. Communication doesn't require physical travel. Radio waves travel at light speed, faster than anything material can go. We can have conversations, albeit very slow ones. A civilization 100 light-years away could send us a message today, and we'd receive it in the year 2126. If we responded immediately, they'd get our reply in 2226, 200 years round trip for a single exchange. That sounds impossibly slow by human standards, and it is. No individual human would live to see both sides of a conversation. But institutions can endure longer than individuals. Universities, governments, and religious organizations have existed for centuries. Projects like cathedral building in medieval Europe took generations to complete, with craftsmen working on structures they knew they'd never see finished. The Long Now Foundation, established in 1996, explicitly thinks in terms of 10,000-year timescales, trying to foster long-term thinking in human civilization. If we can learn to think on these longer timescales, interstellar communication becomes feasible even at light speed. A galaxy-wide conversation could emerge, a vast network of civilizations exchanging data, science, art, and philosophy, even if no two civilizations ever meet in person. Each message would be carefully composed, knowing that the response won't arrive for generations. But the conversation would continue, accumulating depth and complexity over millennia. We've already started this process, albeit tentatively. In 1974, astronomer Frank Drake used the Arecibo radio telescope in Puerto Rico to send a message toward the globular cluster M13, about 25,000 light-years away. The Arecibo message was a simple binary signal containing information about humanity, our numbering system, atomic numbers of elements important for life, the structure of DNA, the human form, Earth's population, our position in the solar system, and a representation of the Arecibo telescope itself. The message will reach M13 in about 25,000 years. If anyone there receives it and responds immediately, we'd get the reply in about 50,000 years. That's longer than modern humans have existed as a species. It's an almost unfathomably long-term project, yet we did it anyway, sending our message into the cosmos more as a symbolic gesture than a practical communication attempt. Since then, we've sent additional messages. In 2008, NASA transmitted the Beatles' song Across the Universe toward Polaris, the North Star, about 430 light-years away. In 2017, the Messaging Extraterrestrial Intelligence Project sent a more sophisticated message toward a star system only 12 light-years away, aiming for a potentially achievable conversation, though still one that would take decades per exchange. These efforts have sparked controversy. Some scientists worry that actively broadcasting our presence might be dangerous, that hostile aliens might decide to attack or invade us after learning we exist. This debate between SETI, the search for extraterrestrial intelligence which focuses on listening, and METI, messaging to extraterrestrial intelligence which advocates active transmission, has become quite heated in recent years. Personally, I think the danger is minimal for exactly the reasons I've been discussing. If hostile aliens exist 100 light-years away, they can't hurt us without mounting an expedition that takes centuries. By the time they arrive, we'd have centuries of warning from their response to our message and from observing their launch. We'd know they were coming. We'd have time to prepare, to leave Earth, to build defenses, to become something they couldn't easily destroy. And what would they gain by attacking? Resources? Every star system has resources, asteroids rich in metals, moons with water ice, solar energy in abundance. There's no practical reason to travel light-years to steal resources when they're available locally. Living space? Building anneal cylinders or terraforming planets in your own system is vastly easier than traveling centuries to invade someone else's system. Slaves or labor? Any species with interstellar travel capability has automation sophisticated enough that biological slaves would be worthless. The only plausible motive for hostile action would be preventive destruction, eliminating a potential future competitor before they become dangerous. This is the logic of the dark forest hypothesis. But even this seems implausible given the timescales involved. If a civilization 100 light-years away observes us in 2026 and decides we're a threat, they'd be responding to our current technology level. By the time they arrive centuries from now, we'd either have destroyed ourselves, solving their problem without their intervention, or we'd have advanced so much that we'd be dangerous opponents, not easy targets. The strategic logic of interstellar warfare is fundamentally different from terrestrial warfare. There are no surprise attacks when your weapons take centuries to arrive. There's no fog of war when all parties can observe each other's industrial capacity and technological level, merely delayed by light speed. The attacker is always at a disadvantage because the defender has home field advantage, all their infrastructure and resources at hand, while the attacker must survive a multi-century journey and fight at the end of a supply line light-years long. So I'm not particularly worried about hostile aliens, at least not ones arriving in response to our radio transmissions. If anything, I think we should be more active in sending messages. The potential benefits of contact, even if it's just information exchange, vastly outweigh the minimal risks. Imagine receiving a message from a civilization 10,000 years more advanced than us. They might share scientific knowledge that revolutionizes our technology. They might offer philosophical insights that help us navigate our current challenges. They might simply tell us that yes, we're not alone, that intelligence and consciousness and civilization exist elsewhere, that the universe isn't an empty wasteland but a place where minds can arise and wonder and reach out to each other. That knowledge alone would be transformative. It would change how we see ourselves, our place in the cosmos, our future possibilities. Right now, we genuinely don't know if we're alone. We don't know if intelligence is common or rare, if technological civilization is robust or fragile, if our struggles and achievements are universal experiences or unique to us. Contact with even one other civilization would answer these questions. We'd know that intelligence can survive its technological adolescence, because at least one other species did. We'd know that our challenges, whatever they are, aren't insurmountable. We'd have existence proof that the future is possible. But contact seems increasingly unlikely, at least in the near term. We've been listening for signals since the 1960s. The SETI Institute has spent decades scanning the skies with increasingly sophisticated equipment. We've examined millions of star systems across multiple wavelengths. We've looked for radio signals, laser pulses, infrared signatures that might indicate megastructures like Dyson spheres. We've found nothing conclusive. The famous WOW signal detected in 1977 remains unexplained but hasn't repeated, making it scientifically useless. Various unusual astronomical phenomena have briefly sparked speculation, like the strange dimming patterns of Tabby's star, but all have eventually received conventional explanations. The universe, as far as we can tell from our observations, looks exactly as it would if we were alone, or at least if technological civilizations are so rare and so distant that we can't detect them with our current capabilities. This could change. The next generation of telescopes, both ground-based like the Extremely Large Telescope and space-based like the James Webb Space Telescope, can analyze the atmospheres of exoplanets for biosignatures. If we detect molecular oxygen, methane, and other gases in combinations that suggest biological activity, we'd know that life exists elsewhere, even if it's not intelligent. That would be a monumental discovery, arguably the most important scientific finding in human history. And if we're really lucky, we might detect technosignatures, evidence of technology rather than just biology. Industrial pollutants in an atmosphere, radio signals, laser communications between planets in a system, infrared signatures of energy production beyond what the host star provides. These would indicate not just life but intelligent, technological life. The problem is that we can only detect these signatures relatively nearby, within a few hundred light-years at most with current technology. The galaxy is about 100,000 light-years across. We're searching a tiny bubble around ourselves, a fraction of a percent of the galaxy's volume. If civilizations are rare enough that they're typically separated by thousands of light-years, we might simply be looking in the wrong neighborhood. There's also the question of whether civilizations remain detectable throughout their existence. We've been broadcasting radio signals into space for only about 100 years. Already, our communications are becoming less detectable from afar. Modern digital signals are lower power and more tightly focused than the analog broadcasts of the mid-20th century. We use fiber optics and cables instead of broadcasting everything through the air. Our satellite communications use spot beams aimed at Earth's surface rather than omnidirectional antennas spraying signals into space. In another century, we might be essentially radio quiet, not because we've stopped using technology but because our technology has become more efficient and less wasteful. A distant observer would see our bright radio signature flare up for perhaps 200 years total, then fade away. If they weren't watching during that specific window, they'd miss it entirely. This is sometimes called the radio windowy hypothesis. The idea is that civilizations are detectable via radio transmissions for only a brief period, perhaps a few hundred years, between developing radio technology and switching to more efficient communication methods. If this is true, then two civilizations can only detect each other via radio if their radio windows overlap in time, accounting for light travel delay, which becomes increasingly unlikely as distance increases. Imagine Civilization A is 1,000 light-years from Civilization B. Civilization A has a radio window from their year 0 to year 200. Civilization B has a radio window from their year 1000 to year 1200. When would they detect each other? Civilization A's signals, traveling at light speed, reach Civilization B 1,000 years after being sent. So signals from Civilization A's years 0 to 200 arrive at Civilization B in Civilization B's years 1000 to 1200, exactly during Civilization B's radio window. What a coincidence! They could detect each other. But this requires incredibly precise timing. If Civilization B's radio window had occurred any earlier or later, they'd miss Civilization A's signals. And Civilization A would receive Civilization B's signals during Civilization A's years 2000 to 2200, long after Civilization A stopped broadcasting, so Civilization A would never know Civilization B exists unless they're still listening even though they're not transmitting. The more you think about this, the more you realize how unlikely mutual detection becomes across large distances. Not only do civilizations need to exist at overlapping times, accounting for the galaxy's 13 billion-year history, but their detectable phases need to overlap, accounting for light travel time. The probability becomes vanishingly small as distance increases. Perhaps this is the solution to the Fermi paradox. Not that aliens don't exist, but that they're simply undetectable by the time we're looking, or we're undetectable by the time they're looking, or we're both looking but at the wrong times or in the wrong directions or at the wrong wavelengths. Two ships passing in the night, neither seeing the other's lights. If this is true, it suggests that even if the galaxy is teeming with life and intelligence, contact might be extraordinarily rare. Civilizations might arise, flourish, and fall without ever knowing others existed. Each might look out at the cosmos, see nothing, and conclude they're alone. The irony would be tragic: billions of minds across the galaxy, all asking the same questions, all receiving the same answer of silence, when in fact they're surrounded by kindred spirits just slightly out of sync in time or space. But let's consider another possibility. Maybe we're thinking about this wrong. Maybe interstellar travel and communication aren't the point. Maybe sufficiently advanced civilizations turn inward rather than outward. Think about the direction of human technology. We started by modifying our external environment, building shelters, making tools, domesticating plants and animals. As we've advanced, we've increasingly turned toward information technology, computers, virtual reality, artificial intelligence. We spend more time in digital spaces than previous generations did in physical spaces. We can experience things virtually that would be impossible physically. This trend could continue. As virtual reality becomes more sophisticated, as brain-computer interfaces advance, as we learn to simulate experiences with perfect fidelity, why would anyone bother with the expense and difficulty of space travel? You could have the experience of exploring alien worlds without leaving your living room. You could simulate entire civilizations, run them at accelerated speed, explore millions of possible histories and futures. You could expand your consciousness, modify your perceptions, experience time and space in ways biological evolution never prepared us for. From this perspective, physical space travel starts to look quaint, like insisting on riding horses after the invention of cars. Sure, some people still enjoy it for nostalgia or sport, but it's not how serious transportation happens. Similarly, maybe advanced civilizations explore primarily in simulation rather than physical reality. They might build Dyson spheres not to power starships but to power enormous computers running trillions of simulated universes. If this is common, it would explain the Fermi paradox neatly. Civilizations reach a certain technological level, realize that inward exploration is more rewarding than outward expansion, and stop being detectable from interstellar distances. They're out there, but they're quiet, focused on their own virtual infinities, not interested in the slow, expensive business of star flight. This is the transcension hypothesis, proposed by futurist John Smart. The idea is that intelligence naturally tends toward optimization, miniaturization, and density rather than expansion and sprawl. Instead of colonizing the galaxy, civilizations transcend into increasingly compact, efficient substrates, running vast computational civilizations in small physical volumes. It's an interesting idea, and it has the virtue of explaining several puzzles at once. It explains why we don't see evidence of galaxy-spanning civilizations. It explains why SETI hasn't detected obvious signals. It explains the Fermi paradox without requiring that we're alone or first or special in any way. But it also suggests that if this is humanity's future, we might not become the spacefaring species of science fiction dreams. We might not colonize Mars and the outer planets, terraform worlds, build O'Neill cylinders, and spread across the galaxy. We might instead retreat into increasingly sophisticated virtual worlds, eventually uploading our consciousness entirely, leaving Earth and physical reality behind not by traveling elsewhere but by departing into inner space, digital realms of our own creation. I have mixed feelings about this. Part of me finds it depressing. The cosmos is magnificent, vast beyond imagining, full of wonders we've barely begun to explore. The thought that we might turn away from it, might choose comfortable simulations over difficult reality, feels like giving up on something important. But another part of me recognizes that consciousness and experience are what matter, not the particular substrate they run on. If virtual experiences can be as rich, meaningful, and valuable as physical ones, why privilege the physical? If we can create paradise in simulation, worlds without suffering, without the constraints of physics and biology, worlds limited only by imagination, why wouldn't we choose that? Perhaps the universe is full of civilizations who made this choice. Perhaps physical space is left mostly empty, while inner space teems with unimaginable diversity and complexity. Perhaps the real action isn't happening on planets or in spaceships but in computations, in data structures we don't yet have concepts for, in digital spaces whose relationship to our reality is like our reality's relationship to a single atom. From this perspective, the speed of light being slow for physical travel doesn't matter because physical travel isn't the point. Information is the point, consciousness is the point, and those can expand and explore in ways that don't require moving matter across light years of vacuum. A civilization might send out messages containing their entire knowledge base, their history, their culture, their collective wisdom. Another civilization might receive such a message and incorporate it, creating a fusion of two intellectual traditions without either species ever physically meeting. This is perhaps the most realistic form of interstellar civilization, not empires of planets and starships but a network of information exchange, a cosmic conversation between minds that never physically encounter each other but nonetheless share in each other's experiences and knowledge. Each civilization would be physically isolated but informationally connected, alone yet not alone, separate yet part of something larger. The speed of light, in this vision, is still a constraint but not a prohibitive one. Information travels at light speed, so conversations still take years or centuries depending on distance, but information doesn't need life support or deceleration fuel. A message can be received and understood even if the sender no longer exists. A civilization could fall, its world could be destroyed, but if their messages survived and reached others, their knowledge, their perspective, their contribution to the cosmic discourse would persist. This gives me a somewhat more optimistic view of our long-term future. Even if we never physically travel to other stars, even if the vast distances prove too difficult to cross with biological bodies or even with machines, we can still participate in something larger than ourselves. We can send our knowledge, our art, our music, our science, our story into the cosmos. Others might receive it someday, might know that we existed, might learn from what we discovered, might be inspired by what we created. And we might receive similar gifts from others, messages from civilizations that might still exist or might have fallen long ago, but whose voices still echo across the light years, encoded in radio waves or laser pulses, waiting for someone to listen, to decode, to understand, to remember. This is why SETI matters, even though it hasn't found anything yet. It's why we should keep listening and keep sending messages. Not because contact is likely in our lifetimes, probably it isn't, but because the possibility of connection across the cosmos, of knowing we're not alone, of joining a conversation that spans light years and millennia, is worth pursuing even if the odds are long. But I want to return to the original question that started this exploration. Why is the speed of light so agonizingly slow for interstellar travel while being so blazingly fast for everyday experience? The answer, I think, is that the speed of light isn't really about light at all. It's about the structure of space-time itself. Light travels at this speed because it's massless, it has no choice but to travel at the maximum speed the universe allows. Anything with mass travels slower. Nothing travels faster. This maximum speed, approximately 300 million meters per second, is built into the fundamental equations that describe reality. But why this particular speed? Why not faster or slower? This is where physics gets genuinely mysterious. The speed of light is related to other fundamental constants like the permittivity and permeability of free space, which determine how electric and magnetic fields propagate. These constants appear in Maxwell's equations, which describe electromagnetism, and their values determine the speed of electromagnetic waves, which is the speed of light. But this just pushes the question back a level. Why do these constants have the values they do? We don't know. They appear to be arbitrary features of our universe, not derivable from any deeper principle we currently understand. In other possible universes, with different values for these constants, the speed of light would be different. In some universes, it might be much higher, making interstellar travel easy. In others, it might be much lower, perhaps making complex chemistry impossible. We happen to exist in a universe where the speed of light has the value it does. And given the size of the universe, which appears to be at least tens of billions of light-years across and possibly infinite, this speed creates a harsh constraint on how far and how fast information and matter can travel. It's possible that this is selection bias. Perhaps only universes with certain parameters can produce stars, planets, chemistry, and eventually life and intelligence. Perhaps if the speed of light were much different, the universe would be inhospitable to life for other reasons. This is the anthropic principle, the observation that we necessarily find ourselves in a universe compatible with our existence, which might explain why various constants seemed fine-tuned for life. But this doesn't make the speed limit any less frustrating for our purposes. We're stuck with the universe we have, and in this universe, interstellar travel is extremely difficult. There are wild speculative ideas for circumventing this limit. Wormholes, hypothetical shortcuts through space-time, might allow faster-than-light travel in a sense, though not through normal space. The mathematics of general relativity allows wormhole solutions, but making them stable enough to traverse appears to require exotic matter with negative energy density, which might not exist or might not be obtainable in useful quantities. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is another speculative concept. It involves contracting spacetime in front of a spacecraft and expanding it behind, creating a warp bubble that carries the ship faster than light relative to distant objects while the ship itself remains stationary within its bubble, never locally exceeding light speed. The mathematics works in general relativity, but again, it requires exotic matter with negative energy density in enormous quantities, possibly more negative energy than exists as positive energy in the observable universe. These ideas are interesting as thought experiments, and they show that general relativity might permit some loopholes around the light speed limit. But none of them are anywhere close to practical with known physics. They remain firmly in the realm of science fiction, interesting to think about but not something we can plan missions around. So we return to the harsh reality. The speed of light is the speed limit. Interstellar travel is possible but difficult, time-consuming, and energy-intensive. Any journey to another star system requires either accepting multi-generational travel times, developing suspended animation, sending machines instead of humans, or transforming ourselves into something that can endure the journey. None of these options are easy. All of them require technologies we don't yet have or social capabilities we've never demonstrated. It's possible we'll never do it, that humanity will remain confined to our solar system for our entire existence as a species. Our descendants might colonize Mars, build cities in the asteroids, terraform Venus, create habitats around Jupiter and Saturn, but never leave the Sun's gravitational sphere of influence, never see another star except as a distant point of light. That would be disappointing in some ways. We'd miss out on exploring alien worlds, meeting alien species if they exist, participating directly in a galactic civilization. But it wouldn't be a bad outcome. Our solar system is enormous by human standards, with resources and living space for trillions of people if we fully utilize it. We could build a magnificent civilization here, one that endures for millions or billions of years, without ever leaving home. And we could still look outward, still observe the universe through our telescopes, still wonder about what's out there, still participate in the conversation via electromagnetic signals, still contribute our voice to the cosmic discourse. We'd be isolated physically but not intellectually or spiritually. Perhaps that's enough. Perhaps the dream of starflight is a dream we need to let go of, at least in the form science fiction has taught us to expect it. There will be no Enterprise, no Millennium Falcon, no fleet of colony ships spreading humanity across the galaxy. The distances are too vast, the energies required too enormous, the timescales too long. But there could be messages, could be exchanges of knowledge, could be the slow building of understanding across light years and centuries. There could be the satisfaction of knowing we looked, we listened, we tried to reach out, we sent our best forward into the darkness hoping someone might find it. Maybe that's what spacefaring civilization looks like in reality, not starships and colonies but messages and memories, not physical presence but informational legacy, not meeting face to face but mind to mind across the vast and lonely dark. And yet, despite all the difficulties I've outlined, despite the harsh mathematics of relativity and the cruel vastness of space, I don't think we should give up on the dream of traveling to the stars. Perhaps I'm being irrationally optimistic, perhaps I'm letting emotion override the cold calculus of physics and engineering, but I believe that if we survive as a species long enough, we will find ways to make it happen. History shows us that humans are remarkably good at solving problems that initially seem impossible. We've split the atom, cured diseases that once killed millions, built machines that think, decoded the genome, connected the entire planet through instantaneous communication. None of these achievements were inevitable. All of them required vision, persistence, enormous investment of resources, and often generations of incremental progress before the breakthrough came. Interstellar travel is harder than any of these challenges, but it's not impossible. It's merely extremely difficult. And extremely difficult is different from impossible. Extremely difficult means we have to be smarter, more patient, more committed than we've ever been before. It means thinking in timescales that dwarf human lifespans, maintaining projects across generations, possibly transforming ourselves to better suit the challenge. Maybe the first interstellar voyagers won't be anything like current humans. Maybe they'll be artificial intelligences, digital consciousnesses uploaded from biological minds, or genetically engineered post-humans designed to thrive in space. Maybe they'll be entities we don't have words for yet, as different from us as we are from our pre-human ancestors. This transformation might be necessary. Biology evolved for life on Earth's surface, in Earth's gravity, breathing Earth's atmosphere, eating Earth's food. We're adapted to a very specific environment, and we carry that environment's requirements with us wherever we go. This makes space travel hard because we have to bring our environment along or recreate it wherever we land. But what if we could change our requirements? What if we could engineer humans who don't need air, who can survive radiation, who can hibernate for years or centuries, who experience time differently? What if we could transfer consciousness into machine substrates that can survive the vacuum, the cold, the radiation, the isolation of interstellar space? These possibilities raise profound philosophical questions about identity and continuity. If we modify ourselves so extensively, are we still human? If we upload our minds into computers, are we still ourselves or merely copies? These questions don't have easy answers, and different people will answer them differently based on their values and beliefs. But I think there's a case to be made that the essence of humanity isn't our particular biochemistry but our consciousness, our capacity for thought and feeling and choice, our ability to wonder about the universe and our place in it. If we can preserve that essence while changing the substrate it runs on, we remain meaningfully human even if our physical form is radically different. And if that transformation is what's required to reach the stars, I think many people would choose it. The dream of seeing alien worlds, of being among the first humans to set foot on another planet orbiting another sun, of participating in something so much larger than individual human lives, is powerful enough that I believe people would willingly transform themselves to achieve it. We're already beginning this process in small ways. We augment our bodies with technology, pacemakers, and prosthetics and artificial joints. We modify our biochemistry with medications and supplements. We enhance our cognition with external memory systems, computers that remember things for us and help us think through complex problems. The line between human and machine is already blurring. Over the coming centuries, as technology advances, this blurring will likely accelerate. Brain-computer interfaces will become more sophisticated, allowing direct connection between our nervous systems and digital systems. Genetic engineering will allow modification of human capabilities, perhaps extending lifespan, enhancing intelligence, or improving physical resilience. Artificial intelligence will become increasingly integrated with human cognition until the distinction between biological and artificial intelligence becomes meaningless. These developments are probably necessary for interstellar travel, but they're also likely to happen regardless, driven by medical applications, military competition, economic incentives, and simple human curiosity about our own enhancement. We're going to transform ourselves anyway. The question is whether we'll use those transformations to reach for the stars or whether we'll turn inward into digital simulations and leave physical space mostly unexplored. I hope we choose both. I hope we develop the technology to create rich virtual worlds and also the technology to cross interstellar space. I hope some of us retreat into digital paradise while others venture outward into the cosmos. I hope humanity, or whatever we become, diversifies into multiple branches, each exploring different possibilities, each following different dreams. Because ultimately, that's what intelligence is for. We arose in a universe that created conditions for matter to organize itself in ways that can think, can experience, can wonder, can choose. We're the universe becoming aware of itself, matter waking up and looking around and asking why. And having awakened, we have a responsibility, perhaps even an imperative, to explore, to understand, to make the universe mean something through our engagement with it. The speed of light is slow. Interstellar space is vast. The distances are crushing and the timescales inhuman. But we're here, we're thinking about these problems, we're taking the first tentative steps toward becoming an interstellar species. We've sent probes to every planet in our solar system. We've landed on asteroids and comets. We've returned samples from the Moon and Mars. We've built the International Space Station, a permanent human presence in space. We're planning to return to the Moon and eventually send humans to Mars. These are baby steps compared to interstellar voyages, but they're real progress. 100 years ago, we couldn't get off the ground. 50 years ago, we reached the Moon. Today, we're planning missions to Mars. 50 years from now, who knows where we'll be? 100 years from now? 1,000? If we survive, if we don't destroy ourselves through war or environmental collapse or some unforeseen catastrophe, if we can mature as a species and learn to think on longer timescales and cooperate on larger scales, then I believe we will eventually reach the stars. It might take centuries or millennia. The first ships might be small and primitive, carrying only microbes or digital minds. But eventually, if we persist, we'll send something of ourselves to another star, and then another, and gradually, over immense spans of time, we'll spread outward into the galaxy. We won't conquer it, that's the wrong metaphor. The galaxy is too vast for conquest, and probably we won't be alone in it. But we'll participate in it. We'll add our voice to whatever chorus of intelligences exists out there. We'll explore not because it's profitable or even because it's practical, but because it's what conscious beings do. We explore. We wonder. We reach outward into the unknown because that's what gives meaning to our existence. The speed of light is slow, tragically slow for our purposes. But it's the speed we have. And somehow, within the constraints of the universe we inhabit, we'll find a way to work with it, to make the journeys that seem impossible, to bridge the distances that seem unbridgeable. Because we're humans, and stubborn optimism in the face of impossible odds is what we do best.